right, well, thank you for the introduction. Welcome back to week 2. So here we are, plein soleil and back inside. So what I wanted to do, I got asked to give, or I understood the instructions to be something relatively introductory. So I wanted to start slowly, since it's Monday morning, and walk back to something we learned about in Ben Michael Coley's lecture. So here is a rather famous knot. This is, I'll call it K for now. This is the Kinoshita-Terasaka knot. This is from an old paper that was interested in creating knots that had trivial Alexander polynomial, I believe. I've put all the, on the sheet, if you look at it, the second page of the sheet has all the old references of different papers that I'm talking about and won't talk about further. So if one of these rabbit holes interests you, follow it as deeply as you like. But here's the Kinoshita-Terasaka knot. And there's a way to produce another knot, which is to single out a tangle and then change nothing outside this disk. So this disk, we're going to do something, but outside the disk, I'm going to make everything exactly the same, modulo my ability to draw things exactly the same. So please stop me if this doesn't look exactly like the same. Sometimes it's called the external wiring of the diagram. And then inside, I'm going to perform an operation, mu, which will stand for mutation. Here, what I'm going to do is I'm going to take the given tangle, and I'm going to roll it over in the plane by 180 degrees. So if I was more careful with the t and picked a scripty t, I could use this to distinguish. So I could, obviously this upside down t, I could flip one way or rotate. And just for the purposes of discussion here, I'm going to rotate. So I've got 4 endpoints to this tangle, distinguished endpoint, and that distinguished endpoint has been sent down to the lower right corner by the 180 degree rotation that will do this. So this is a planar operation. Of course, you think of it as a spatial operation. I guess it's a good moment for a disclaimer. I'm going to talk about knots with making no distinction between the knot in 3 space and a choice of diagram. So there's that wrinkle through everything I say. And now, if I do roll this over by 180 degrees, I believe I'll end up with something that looks like this. OK, so the result I'll call K upper mu, and this is the Conway knot, or Conway's mutant. And so this shows up later. Well, Conway was working towards an enumeration of knots by starting with tangles and various operations on tangles that combine them via addition and multiplication, various rotations. There's a description in Colin Adams' book about how Conway was building this up, if you don't want to go to Conway's original paper. And so what I want to term Conway's reassembly problem So the observation you should make is that these should appear to look like they're made out of roughly the same building blocks. I have various smaller, simple tangles known as rational tangles all assembled together. But I've decided to glue 2 of these rational tangles assembled into this tangle in 2 different ways. And the question is, when you do this, do you get distinct knots? So are K and K prime distinct knots? And what's, I think, pretty about this question is that it's really difficult to answer. So in, I believe about 1977, sorry, 1970, the Conway's paper appears after this, but the work was done before. So Riley showed that in fact, K and K mu are certainly different. And how did he do this? This was by counting finite representations of the fundamental group of the knot. So of the knot group, just in case that terminology is new, so this is the fundamental group of S3 minus a neighborhood of your given knot. In particular, so specifically, what happens to work for these knots is representations to these groups LP, so groups that are PSL to P for some prime. And I think why he was looking here traditionally is that L5 is the alternating group, A5, and Crowley had shown that that was a fruitful place to look for representations to distinguish knots. And this is still a technique that's in use today for a lot of the tables. You're building tables, you add a new knot to the table, and you ask, is it new? You start looking at the finite representation. So it's a method that's sensationally good for separating knots in general. But what's great is when this was happening, so this is really early days of computer programming. I think Riley was grinding this out in either Fortran or Pascal. And if you ever have occasion to go to University of Southampton, there's plots of Riley's work on the walls that are, I mean, to the mathematically inclined, beautiful to look at, I think. Okay, so something that we learned about in last week, very briefly, is that there's work of Gabay that comes later, 1986. And contained in this work is the fact that K and K mu have a different Seifert genus. So this is the minimal genus of a Seifert surface with boundary, the knot. One is 2 and one is 3. I forget which one. Somebody here probably knows right off the bat. But this is another fantastic way to distinguish knots. It's just not obvious that these have different Seifert genus, and this is the machinery of sutured manifolds building up that does this. So very different techniques, and you know, show you that these tools really look deep into the problem. These are these classic easy to state questions with hard solutions. Okay, so now for notation. I'll write K for some knot. So not just this Kenoshita-Terasaka knot, and K mu for any mutant. Okay, so this is somewhat ambiguous. The point is it's supposed to be clear from the context. Maybe a remark is what's ambiguous here is there are actually three mutations that are possible. So just to be clear, and maybe for a bit of foreshadowing, I'll continue to use this star to distinguish which of the mutations I've done. So there's a mutation that rolls around the x-axis. So that should take a given t, and it's still going to flip it upside down. But this is the one I didn't do before. So that's taking the upper left, just flip it to the lower right. So the x-axis is the usual x-axis from calculus along the blackboard. Mu y, using the y-axis. Right, so that's totally indistinguishable when you use the letter T for tangle, necessitating an indication of the endpoint that switches. Okay, is everybody happy with what this is telling you to do instruction-wise? I'm cutting out a disk, and then I'm applying whichever flip 180 degrees of the available axis so that the star is taken to the appropriate place. And then finally, the one that I used, or the one that Conway and Kinoshita Terasaka requires, is this flip, which rolls around an axis that's perpendicular to the blackboard. And I'm going to be really, again, we'll say which one in any given context, but these are all three possible mutations to obtain a mutant knot from a given knot. So the first step is a choice of tangle, and then applying this operation. OK, so maybe something to note. The second remark. Yep. Yes, and they're not all necessarily distinct. Like for certain tangles, there'll be a symmetry inherent, and sometimes these are the same thing. But yeah, once you fix a knot and then you fix a tangle, there's 3 different mutations possible, and we'll say which one when it matters. But when I want to talk about a mutant pair in general, say K and K mu, what I'm asserting is that K and K mu are related by some choice of tangle, some choice of mutant operation. Okay. And I guess hopefully it'll become a little more clear why sort of, getting into the weeds is not so important. So the second remark is that the above tools, as far as I know, are not guaranteed to separate any given mutant pair. I will say that I think in practice, these types of tricks seem to work phenomenally well. But I'm not sure that there's a proof that will always work. Though if people are interested, I think this business by Lackenby and Alan Reed and many others about profinite completion starts to probe in that direction. Not at all my area of expertise, but certainly something you can read more about if you're interested. And just to send this point home a little bit, here's an entirely different set of examples. So bear with me a moment. The important thing is that this not be alternating. So if the knot is not alternating, tell me. Here we go. There's a knot, K. Here's a tangle, T. And the mutation I'll do, again, apply mu z to get K mu. OK, another example pulled out of absolutely nowhere, but something that I put on the exercises for people who are thinking about Heegaard Floer homology. So that's the hint. You should apply a very powerful tool here. You can show that K and K mu have the same cipher genus. Yeah. I hope so. Oh, it's not. Great. Thanks, Pamela. I really appreciate it. So let me fix that. So is it alternating over here? Over, under, over. Under. Great. So the problem is in here. I will fix this. We can fix anything. Yeah, so I have nothing to say about the example that's not alternating. Again, strong hint on how to do the problem. I mean, how do you find the genus of an alternating knot? I mean, I guess you can do that directly. I don't know. Stop giving the hints away. Actually, that I don't know. I don't know. Is it? That's still using a tool that we're like. The hint is still to use a tool that I'm not going to talk about. So Paola's doing the exercise in real time. I'm not going to compute the Alexander polynomial. Okay. Fun. Okay, but finally the fact here is, and this is not so different in spirit from Riley, is that if you're interested in symmetry groups, so that is the mapping class group of the knot exterior, the symmetry group of K is not isomorphic to the symmetry group of K mu. So you can just count the elements in the symmetry group and they're different. And this is similar in spirit because, well, for alternating knots anyway, the symmetry group is counting outer automorphisms of the fundamental group. So this is, I gave you a reference to where this sort of gestured at explicitly for this example, but this sort of fact, the fact that the symmetry group can see the difference between mutants is, I did some digging. I believe this is somewhere buried in Michel Boileau's thesis. Okay, so there's some background on mutation. I think that mutation is interesting because, in fact, a great many. I didn't. I mean, I kind of did anachronistically. I'm claiming this is true, that you can diagrammatically, you can work through what the symmetry group of these two knots are. This is telegraphed somewhat. You see there's a strong inversion on that knot? Oh, I don't know. I did not try. I bet yes. But in a sense, you are, because here you're counting outer automorphisms of the fundamental group. So that's, I don't know. To me, that's a representation theoretic problem. So yeah, it's in the same spirit, absolutely. And yeah, is it in the tables, this knot? I mean, I don't know. You can generalize it and make it big enough that it won't be sitting in the tables. Then you have to think to yourself, what would you do? And that means you would actually sit down and calculate brute force the way Riley does. Presumably, yes. But the problem is, I don't think there's a certificate that it will. Great. So many, I would say, powerful invariants are, by contrast, are known to fail to detect mutation. And so, for instance, if you look at the volume of the knot, the hyperbolic volume of a knot, this is known to not detect mutation. That's a result of Daniel Ruberman. And a much more recent result is that if you look at the dimension of the knot Floer homology, this is something fancier, but I'll just say it in terms of the dimension, Z mod 2Z coefficients. So that's something that you can count. This is also a number that will not see mutation. And this is a result of Zabrovius, who I saw out for a run this morning. He's not yet here, probably because I told him not to come. But you can ask him about this. And there is overlap with what I'm talking about and these kinds of tools. And he said he'd also be available in some of the tutorials as well. So you can ask him things about what I'm lecturing, but also about certain tangential issues as well. OK, so my view on this whole thing, which I offer with exactly no warranty, is that mutation is something interesting because understanding when an invariant fails to see mutants is really telling you something about a possibly hidden symmetry about the invariant you're studying. And so what do I mean by that? An instructive example to explain somewhat what I mean by that, a symmetry in the definition of in an invariance definition. Comes from studying Kaufman's bracket. That's definitely spelled wrong. Probably two F's, right? Well, you know, but there's two somethings. And it's not two R's, two B's, right? Two R's? Two what's? Oh, no. My spelling is horrible, and I apologize. Okay, so Kaufman's bracket. So what is Kaufman's bracket? So what this does is it applies rules to a knot diagram. The first rule, so knot brackets, this is like regular round brackets for number one. So the first rule is that if I take the bracket of, and make these a little smaller, there is a difficulty on the blackboard about round unknots. Unknot with no crossings. So we're going to just declare that that should have value 1. Okay. And then there's the extremely important divide and conquer rule that if I see a particular crossing, then I should replace it by, first time you'll ever see a capital letter used for a variable, and maybe the last time. There's the rule that allows you to remove crossings. So you fixed a diagram, you can zero in on one crossing and change it in 2 different ways to get 2 different diagrams with 1 fewer crossing. So this definitely gives you a divide and conquer strategy. And then the last thing you need is how do you rub out additional loops? So when you see any given link diagram plus unknotted component with no crossings, this gets this mysterious loop value. And that multiplies the same bracket, but without that closed loop. And so what you get if you take a diagram and you apply this recursively until everything is replaced by algebraic values is you'll get something called the bracket of your choice of knot K. Okay. Choice with a fixed diagram. You're not allowed to change the diagram through this process. This will give you an element in the Laurent polynomial ring with integer coefficients in A. Okay, great. You can check that this bracket operation is invariant under 2 of the 3 Rademeister moves. So under Rademeister 2 and Rademeister 3. Of course, that suggests what the first example I should run through if you haven't seen this before. So here's a single crossing unknot, which I can't just replace with a 1 according to these rules. So apply my divide and conquer algorithm. And that's going to, so that the important thing is which crossing I have, right? If I rotate this by 90 degrees, I'm going to switch the roles of the resolution. So the key thing is to really fix your diagram from the start and then apply this rule. And here's what happens. So again, I won't highlight these every single time, but there's the particular tangle where this operation happened. And now I can continue working through this. So I can move one of these components at the expense of adding the loop value. And then this will have, oops, that's a -1, so a -1. So there's an entire term where I've factored out a single loop. I did 2 steps in one. I mean, soon it'll be Monday afternoon. I'll have to move a little faster. There's what it is. This is equal to 1, and then I can arrange terms and cancel something in here. There'll be a minus a to the -1 and an a to the -1 that are going to cancel. And I'll end up with, as long as I didn't mess anything up, a cubed, which is a Laurent polynomial. In fact, it has the problem that it's not this Laurent polynomial, which is the Laurent polynomial associated with the unknot. So this is the problem that is a little bit, I don't know, irritant. But it's not that big of an irritant. If you're used to the Alexander polynomial, the Alexander polynomial is a geometric definition, has the order of a certain module associated with the universal abelian cover. It's only well defined up to units. And really buried in here is that there's a theorem that I think is useful in its own right. So Kaufman was trying to, I really think it's 2 Fs. Kaufman building a simple diagrammatic reformulation of the Jones polynomial, but along the way, what you get is that this bracket is a non-invariant up to units. Solve the multiplication. By units. So what do the units look like? Well, they're like plus or minus a to the plus or minus, well, I won't write it as plus or minus, that looks ambiguous, k in z a inverse, where k is k is any integer. Okay, so this is not for people who have thought about the things that are coming, like homological invariants of knots. You know, you could ask for something to be absolutely graded or something to be relatively graded. And here, this is just your polynomial up to a shift. So it's telling you that you don't really know what the powers are, but you know what the powers are relatively. And really, it still means that the coefficients and the list of coefficients in order with all their zeros in between, that list is a perfectly good invariant. And in practice, I think it's quite a strong invariant. It's capturing a lot of the Jones polynomial. But if you want, and this is just following exactly Colin Adams's construction of the Jones polynomial, which is really direct and pretty, you can use a choice of orientation on K. And the writhe of the diagram, and the writhe of this oriented knot to remove this units ambiguity. And in doing so, recover the Jones polynomial. The key thing is that you're just a normalization away from the Jones polynomial at this point. OK, so there's the Jones polynomial in a whirlwind. And what I wanted to do is, right, this symmetry business. Right, so what's really pretty about Kaufman's approach is that it's entirely local. So this is implicit here. If you're going to apply a Reidemeister 2 move, you have to single out part of the diagram where there's a Reidemeister 2 that you can change and resolve on one side, and then check that you get two equal quantities. Same thing with Rademeister 3, except there's a nice trick where you apply Rademeister 2 in order to get Rademeister 3. So you're working locally. And again, the way I circled things here, you really are singling out crossings or collections of crossings at the outset in order to organize and apply these rules. So this really is a local process. And that is to say, I could write maybe I should stay with the color coding for now. This makes sense somewhere. Color coding. Okay, so I can't resolve further, but I do get an expression in terms of simple crossingless tangles. Right? So this, in general, given some tangle T, we'd get something that looks like T input, some term involving this symbol, bracket of the crossingless tangle that joins the northern points and the southern points. And then same thing, but with the points in the two hemispheres, eastern and western hemispheres joined. And now you won't just get an inverse, you'll get some polynomial, that's the polynomial associated with one resolution and the polynomial associated with the other. So when I don't use the electronics, am I ruining the boards slowly? No, it's good design principles. Okay, so you don't land on a polynomial, but you land on something that we can say something organized about. So now, it's not a Laurent polynomial. It's a pair of polynomials, but those pairs, those are the coordinates somewhere. So rather, it is an element of the skein module, which I'll write as S. So we're only thinking about the skein module for these particular collections of tangles. So what is this? Is the module, coefficients in the Laurent polynomial rings, generated by all tangles footnote coming, generated by all tangles modulo the ideal generated by the pair of local rules. So I can replace crossings in a tangle diagram and get something more complicated in terms of how many terms you need, but less complicated in terms of how many crossings are involved in the diagram. Okay, so this is exactly Kaufman's rule number 2. And then second, if I've got a tangle and then somewhere there's a closed loop that doesn't interact with the tangle, I can remove the loop And as long as I put this value in, still get this. Okay, so here's two rules that I can apply everywhere and divide and conquer and give a new expression for my element t inside this scheme module. I have to be a little careful with Reidemeister 2 and Reidemeister 3, so now let me say something about the footnote. So what are we really generating here? I'm giving a diagrammatic definition, or maybe gesturing towards a diagrammatic definition. And there's a really beautiful, the paper by Rolfson that I referenced gives you a nice, gentle introduction to this with lots more references. So the tangles are up to planar isotopy. R2 and R3 are allowed, but evidently you have to be careful with Reidemeister 1. You have to resolve those out and add the loop values in, just as is suggested by this example. So if you want to be careful in some other way, you can do that, but this is how you get there. I think the key fact I want to pull out of this is that T, sorry, so T in this skein module has a unique representative with coordinates let's say P horizontal resolution of T and P vertical resolution of T. Okay, so this is just the process of applying the rules at every single crossing and then rubbing out closed components so that you arrive at this expression. So that's giving you something invariant associated with a tangle. Coordinates. And the beautiful upshot here is, I guess yeah. Pardon? One more time. Yeah.
Only two of the choices determine the other.
Which two? You mean this choice, the choice 2?
I don't understand correctly, but you say that the tangle is the sum of polynomial times.
Oh yeah, you have to apply. I mean, you have to show that this is independent of which order you do it, but you have to apply this at every single crossing. So that's what happens for a 1-crossing diagram. For a 2-crossing diagram, there'll be 4 terms. You have to sum them together and do some more simplifications.
Okay.
For a 3-crossing diagram, there would be 8 terms. It gets bad fast.
You have to record all of them.
Yeah, you have to record all of them. But the excellent question. I did want to mention this. Note that, and this is another thing that's implicit in Kaufman's observation. You're fixing a choice of diagram. That's in everything that I'll talk about, that's a choice that you've made, and it's something that downfield you have to show invariance of that choice. But when you build this data where you you number all the crossings, and you make a choice of a pair of resolutions at every single crossing, if you keep track of that in a big cube, which Kaufman did, that before you turn that into anything else, that cube of information, you can move between your particular diagram and that big cube of information, that somehow those are both the same type of diagrammatic information. That need not make any sense right now, but that's what's going on philosophically under the hood here. But yes, you have to show independent of the choice of ordering on the crossings and so on and so forth. So this exercise is going to look innocuous, but there are some things to check. So that is that due to the symmetry, So because this is the mutation symmetry, right? So any given mutation fixes the two basic crossingless tangles. So because of this symmetry, the bracket of T mu is the same as the bracket of T. And if you choose orientations on your knot on which you're doing mutation, then you'll get that the Jones polynomial famously does not detect mutation. And the reason I'm going through this background is this is to some degree the book proof of this fact, right? After you see the Jones polynomial from this perspective, it has to be mutation invariant. It has to be mutation invariant because this object has this particularly beautiful symmetric basis that is mutation invariant. And that's like, you know, this is one of those statements, like depending on what you know, something's obvious. This is the right way to see what's going on. And so the reason I wanted to use that as a setup is because what the lectures I want to talk about are really based on Barnaton's ideas for categorifying this perspective on the Jones polynomial. While I'm erasing, are there questions? Okay, so sort of where I thought I'd be. You go.
So is this a model with and then if you wanted to map to, like if you filled in the graph, you would map those two generators to polynomials, and then you get an infinite map that way?
Yeah, well, I've erased my examples. But once you fix this disk, you know, what I called the external wiring is also a tangle. So it depends on what your order of operations are, but you can work out what this the bracket of TR for the inside and the outside, and then pair those together in the appropriate way. There'll be some extra circles to rub out because of at least one of the 4 ways of reassembling those is going to generate a loop. But yeah, that's the reassembly required. So there is something to do, but you're only switching the outside staying fixed and the inside is changing, and so you really need this information plus some hand-wringing about what happened to the writhe. And if you don't know what the writhe is, also looking up what the writhe is and learning how to calculate that using a right-hand rule and so on and so forth. Okay. Again, for people that have never seen this, the right place to quickly get up to speed with it is to look at the relevant chapter in Adams's book. It's really to the point and elementary. Okay, so the idea that I want to talk about, promote, is to view, maybe I should say Barnaton's idea. Is to view this data, so this crossing resolved one way and the next, together with the saddle, which moves you between these two crossings in time, as a chain complex. Okay. And eventually the notation will be a different style of bracket. So double square bracket of T will be what we call this. And that's, in this case, I've taken the information for the crossing, the single crossing example, So here's the two resolved pieces, and the idea is to join them up by something that's in the, say, the disk times I, and this saddle move that moves between those two things. And deciding how one should see this gadget as a complex is actually an incredibly ingenious idea. So what Barnaton does is he introduces a category, Cobb. This has objects that are crossingless tangles. So that is to say, things like this, perfectly good crossingless tangle, so it can have closed components. And the morphisms, yep. All of my tangles have 4 endpoints. In fact, all of the objects for the rest will have 4 endpoints, and that will be important for a coming exercise. So the morphisms are, I'm fixing a field, k linear combinations of cobordisms. So for example, what might one of these look like? So here's one. I'm not going to draw many cobordisms, but I will draw one of them. And the reason I made some space here, because the cobordisms can have closed components, the inside part and outside. And this is, my convention will be that this is a morphism, and it's going from a tangle on, oops, I guess this is meant to, again, probably won't stick to this color coding for the rest of time, but for today, we try. Here there's a tangle on one end that has the 2 components going to the boundary and a single closed component, and on the other end, it's switched to the other tangle, and the closed component has been erased because it joined up using some saddle move here. Okay, so that's the kinds of morphisms you get. But again, just like in Claire Amiot's lectures last week, this category is souped up. It's enriched over vector spaces in the field K. So linear combinations of these things make sense. And the reason I need linear combinations is I have to add a couple of, I'm going to erase this. Yeah. It's
So I will do a practical version. You can either, if you want to make a cobordism, forget about this first component. You can first decide to glue the first component to the up strand and then connect the 2 strands, or do the opposite. You connect the first component to the lower strand and then connect the 2 strands.
Yeah.
That's the same cobordism, but the physical point is kind of the same.
Yes.
You want to consider that the same.
No. They're cobordisms up to isotopy and change from time. So this is, yeah, that's true. So thank you, Paolo. So isotopy classes of cobordism with boundary fixing isotopy. So the information at both ends is fixed, but in between you can reorder critical points and so on. Okay, so we need to introduce, so there's a sub L for local relations to get a category with fewer morphisms that's called Cobb sub L. So here's the rules that I need. So the first one is Barnaton's sphere relation. So if I see a closed component that's a sphere anywhere in my cobordism, that sets the entire cobordism equal to 0. Okay, that makes sense. I have a 0 in the morphism space because I'm taking k-linear combinations. Okay, importantly, this is not a closed loop, right? This is 0, and this is just a blackboard problem with, I don't want to cross it to tell you that it's 0 because it's not the empty set. Okay, empty set and 0 mean different things here. It's just an annoying fact of the landscape. And then there's this four-tube relation, which is going to feel a lot like a skein relation from before, but it's a skein relation that relates linear combinations of cobordisms. So I may see a piece of a cobordism that looks like a macaroni noodle, and then elsewhere there could be a pair of disks. And now I'm going to give you a shorthand for thinking about what I can do here. So I'll use these two pins that stop for the disks, and then arc going through the noodle. And now I'm going to rearrange these in different ways. So I can have a pair of things that are going to be equal to another pair of things. And the pair is that I can remove the noodle and attach it to the other side. So that sum is the same thing as the sum that joins top to bottom with the noodle and caps the remainder, or the right-hand side is capped and the noodle is attached to the other side. So just how does the shorthand work? That's the noodle, and I've got disks here and here. You can fill that in for every single one. Okay, so this is Bonneton's four-tube relation. It's telling me that if I see this configuration anywhere in a cobordism, I can replace that by the linear combination that's these two cobordisms, so the local change to the general cobordism minus this local change. An interesting exercise here is that if this uses the fact that we have a closed sheet in a specific way. So if I have a cobordism here running this way, so I've got some closed component, I'm ignoring that, and I see a closed torus. So for example, this cobordism here, the claim is that this is the same thing as 2 times the same cobordism, but with the torus removed. Meaning this cobordism here is equal to 2 times. So if I call this is equal to 2 times that given surface. Okay, so it turns out that this follows from these two relations. So Bonneton adds the tube relation, the torus relation, which is that a torus anywhere in your cobordism has value 2, so that also decreases the size of the morphism spaces. But we have a closed component because we're working with tangles specifically. So the exercise shows that that in fact these two relations together imply T. Anyway, that's people who are opening Bonneton and seeing that he would add this at the outset. There's a nice little thing to do here. I'm not going to say more about the exercise because we can talk about it during the tutorials. Yeah. What is T? Bracket T?
No, the relation.
This relation?
No, when you write first U plus S, it implies T.
Yeah, so these are two axioms. I have to quotient by this to get the morphism spaces in Cobb mod L. Yeah. And there's, right? T is this rule. But round bracket T, totally different from angle bracket T, totally different from double square bracket. Yeah, I know you know, but there's a huge force of terrified people over on this side because the notation is going bananas, and like this is like the mellow introductory day. So we're gonna go, we'll take a breath, we'll sleep on it, and it's gonna be all right. But anyway, I'm just gonna overuse the terms like the letters T and K a lot. Yep. It could be knotted up. And yeah, so you could use this cutting relation to get rid of things. That doesn't, yeah, there's another issue you could we're talking about embedded or immersed or embedded or abstract cobordisms. Gadnout, so a student of Barnaton's, showed that actually you can work with embedded cobordisms. Things simplify quite a bit. There's some work to do there. I'm not saying that it's obvious, but yeah, you can, yeah. Well, I don't know how you would, but you can, yeah. I don't know how you would work with that. See, the whole point is we're building a diagrammatic here for the morphism spaces, right? This really should feel like a skein relation where I'm allowed to change a crossing and replace it by these two simpler diagrams. It's not clear, but at certain times, this is going to allow me to simplify a cobordism. In fact, this exercise is showing you that you have to find the noodle, pick a couple of disks, and then look at the pictures that result. And something's obviously simplifying here, right? I can get rid of the torus up to a coefficient. So there is a feel of a skein relation sitting here, even though it's operating on the morphisms. Okay, let me, moving along here. So I'm not going to say what complex means yet, but I want to end with at least a sanity check. In order to set up the exercise that I set, and then we'll talk about that this afternoon. Or I expect that will be one of the things that we talk about this afternoon. I'm going to try not to do this, but today I'm going to go over by like 3 or 4 minutes. Marco's going to give the time back to you. So the expectation is no matter what I do here, the tangle that I get from, say, a vertical resolution. So that's some complex. Don't know what it is yet. If I'm going to get an invariant, it should be homotopy equivalent to a chain complex that I get by doing a Reidemeister 1 move. All right. So if these are chain complexes, then there should be a chain homotopy equivalence. Okay. So now let me tell you some things. Okay, that as a chain complex, it can only really be one thing. So this symbolically should feel somewhat tautological. There's a 0, I'll try to make those small. And then there's an object in the cobordism category, and then a 0. That's a chain complex. The maps are 0 maps, so everything's squared to 0. Great, it's made out of pictures, but let's work with that for a second. Now, this object with the single kink, well, I have to apply a Reidemeister 1 move here. So this is going to have more than one term in it. And the first resolution is this. Oops. And the a inverse resolution would give me this thing. Okay, so again, I'm taking my desired object and I'm flipping it around backwards at this particular point here. Okay, and then this has a saddle. So I'll just draw that as a shorthand here. There's a little saddle that joins this disk in there, and that's what I want to interpret as a chain complex. And the only really mysterious choice I made here was that I decided that to just put these in the same cohomological grading, and we'll just take that. I'll tell you where this came from eventually, but we're hoping that something of this form admits a chain homotopy equivalence. So what should that mean? So here's the cheat sheet. So basically, we want to understand, well, how does Reidemeister 1 work if it's going to work at all? And what I want to show you is that somehow these additional relations become essential right off the bat, even if you're just hoping that these can be chain complexes in some way. So I don't really have to worry about on the right. So I'm just going to draw the left-hand part. Okay, so this is a closed loop, so we'll make it bigger. All right, and here's D. And then there's going to be an F map and a G map. And then there's 0 maps everywhere else. And I'm also going to need a homotopy H. And so now let me write down the D, G, F, H. So D is actually D1. Sorry, G, D0. G is actually G0. All the other GIs vanish. F is actually F0. And H is actually H upper 1 if you're indexing things correctly. Okay, so let me tell you what these cobordisms are. So D, we know what it is. This is a cobordism that takes a handle and attaches it in to that sheet that's running along. Right? Everything is running left to right. G, that thing just takes, actually just caps off that disk. F is more interesting. We'll put that in a second. And H, it also adds a little cup. So it's running from this thing and we'll see why that has to be in a moment. Okay, and then F is actually the linear combination. Let me just make sure I'm not off track here. Otherwise, it's just going to not at all work when you open up Biton. Great, so F is a funny linear combination. It's got, yeah, it's disconnected. It's got a sheet and a right, because it goes from the sheet and then it births a circle. And then here's a linear combination. So a torus into, right, because this is going from the top to the bottom. So I have to birth a circle in some way, and I do this in a strange way. One is with a saddle, and one is by having a torus component. Okay, so what I want, and I'm going to leave it to you to check that this actually gives you a chain map. So if I do F and then D, I better get 0. Okay, that's something you can check. The key thing to check is the homotopy. So let me do the direction. So what we want is identity minus, it's the G then F direction. So GI composed with FI. This should be, I just want the indexing right. H first. HI plus 1 composed with DI plus first doing di minus 1 composed with h I. Okay, does that look familiar? That looks like a homotopy equivalence. So now let's so we're trying to compare F and G composed together. F and G composed together should go from F back down to G first. So up, and then down. And this is the I equals 0 spot. And then there's also an I equals 1 spot. And this is D. And now H is running back this way. So this should look like a chain homotopy equivalence now. And what's going to happen? So here's what we'll do in the exercise. We'll see that this has one term. Okay, this is now going to impact to give two terms. Doing D and then H is something, so this will have one term. But then doing H first, which is nothing, and then D, this will have 0 terms. So I'll have a linear combination of 4 terms, and then what we'll do in the exercise this afternoon is we'll use for TU to show that this actually gives a sum of 4 things that sums to 0. We'll just try to build the 4TU operation out there. So if we can make this work, so if we can make these indistensible complexes that have sensible chain homotopy equivalences between them, you cannot work in Cobb. You have to work in Cobb mod L. Already, well, secretly in checking some of the other things, the T relation, which is equivalent to S, so the T relation becomes essential, and the 4TU relation becomes essential, and we can talk about that more. Okay? That's where I'll stop. Apologies for going over.